I don't give you the script right off, but tonight, again, I will give you the script so you can sort of practice this a little bit more. Especially when it comes to, this is mainly to get you ready for the structure of how we put these packages together. Remember that a lot of times we're going across different estimation types, but they all have a general setup in the sense that we have the data. We have to tell it what type of model we want to run. In this case, we're using LM. That's the OLS. So now it's the packages are getting ready. So once it has LM, it knows to expect a dependent variable, the tilde sign, and then your covariates as it goes across. Then you'll notice that you had to go one more step because when you load it, if you've loaded other things in there, you're going to notice that there's a lot of things on the right-hand side. It sees all those, but it needs to know which one to use. So most time we put the comma data equal to, so it knows which data set to use. This is what I meant by it's a little bit more structured than what you get with Stata. Most of the time you just tell it to run this because you see it and that's what the data frame is. Here, you can hold multiple data frames. So you need to be specific on what you're running. Okay? And then, so most of you made it about halfway or so, so we'll just kind of fill in the rest as we go. Let me just get it over to that side.
So if we want to tabulate the results, can we use cable?
Cable is one of those you could use. It's mostly what you become comfortable with. Cable is one of them that is used a lot, but I tend to use for standard OLS regressions, standard type models, I'll use Stargazer instead. Just because it's a little bit easier to use sometimes. It doesn't take as much what we call ordering, because in cable you have to tell it, this to make sure it stays in a nice format. So, but the thing is it only comes with practice. And the thing is, there's one called text reg, there's one called screen reg that I know of, and it just depends a lot on what you're doing or what models you're using. So I don't want to say that you only use this one or you only use that one. You're going to find that you're going to need to be a little bit more versatile in which ones you're using. Yeah.
Can I just ask for some quick?
Yeah.
It's just like a formatting thing. I just wanted to.
Let me go through this and then I can do the formatting thing. So I just want to try to, just so that we don't spend too much time on this, I need to sort of continue on with it. So when it comes to some of the stuff that you should have done in this, I'm just going to kind of go through the code. You'll notice that in this case, I'm also showing you the earlier stuff that I did, where I did the simple regression, but then I graphed it so that you could see that nonlinear relationship. I'm trying to make sure that I include all in my code so that you can take it home and sort of practice it, because it's about being able to tell your results to whoever the reader is. So for this one, let me just find it real quick. Okay, sorry, I'm not sure exactly where it is in my code. I want to put it at the bottom, just in case you're looking for it tonight. It's something, for some reason it didn't print. I'm just going to put it here. Okay, so the first thing we should have done when you were doing this is basically load the library for Wooldridge. Then basically you call in the GPA 3 using the data with parentheses. When we run the first model, the structure is basically LM parentheses, your dependent variable, sats, H perspect, and total hours. When we run this model, if you run it without putting it as an object, you're just going to get the coefficients. It's not going to spit out the rest of it. Remember, it's all about inference as well. So if you want everything, you need to basically store it as an object, or you could add some things to the original to get that information out, but it's better just to store as an object, and then you can summary for that to actually get the results. It gives us standard errors for the the t-stats and everything. When we do the second one, I was asking about the interactions. There are multiple ways to do this. You can create the variables yourself, or you can ask R to do it for you. We can do that with a little asterisk, putting it between sat and female. Now, if I had actually taken out these parentheses and just put this in by itself, it would actually have understood to put in sat by itself, female by itself, and then include the interaction. So it would do that for me as well. But if I actually want to specifically show it, I can basically tell it to basically do this and nothing else. That's what the I is sort of telling it to do. Don't create additional variables, only create what I've told you to create. Then I can do that for HS perspect as well, interacted with female, and the same with total hours. And then I could actually print that again. Okay. If I want to take a little further, remember for any type of F-test, when we're doing a joint test, we have to have our restricted versus the unrestricted model in this case. So one of the ways of doing that is basically taking just a restricted model that does not include any type of interaction. It only maybe includes a dummy variable for female, but no interactions between the rest of it. And then basically I could test it. Now I kind of cheated by using the ANOVA package in this case, but I could have done it by hand as well to get a statistic out that tells me whether I should or should not be using that particular specification in terms of the interactions. And then the last is just creating, in this case, season binary variable. Now, one thing is you need to make sure that R understands that this is binary, 0, 1. Sometimes if it's loaded in as a factor or a categorical variable, it messes around with the model. So sometimes you need to make sure it's numeric. So instead of actually using the season variable, what I did was I created a new variable to make sure that it's 1 and 0, so I know what it is. Once I do that, I run the same LM model, but I just put season binary as the dependent variable. Okay, and then I had a SAT, total hours, cum GPA, female, black, and white. Okay, and then I could run that model. Now these are all the different ways to create the interactions, do little tests in terms of whether I should be including that distinction. And then these are all ways of summarizing these models as well. So if I actually run this, as long as there's no problems with the packages, let me see if it runs. Then it should produce all the results that we were looking for. See, and this is one of the benefits of actually calling in an object. When you call an object, so when you print it out just from running the command, it's going to spit out whatever is the default information. Most time we do that to look at the coefficients and nothing else. But if we need the more statistics out of this, what we're going to need to do is basically create an object so that it stores this information. Because when you do this, it's actually storing all that information over there as well. And that's the good thing. You might need that information to help you out. You need the residual sum of squares to basically try to understand whether including or excluding certain interactions are improving or kind of reducing the amount or the SSR in this case. So these are all things that basically make it a little bit easier. So it's not just about running the regression sometimes, about the information that's also stored within inside. So I have the residual standard errors. I have, I know the number of degrees of freedom. I get all this information out of by storing it. I know the F-stats, and I know how many regressors I had. In this case, 3. Then you add 1, that you get the degrees of freedom. So all that information is stored. It's just meant to be an example to get you sort of familiar with how to construct a regression. Because remember, that's the key. We want to describe everything like we were yesterday, but now we also want to run something as well, to model something. So we have the visual aspect, but we also have the regression aspect as well. Just remember, so I'm going to save this script file and put it in that folder tonight. Just remember that it's at the bottom because I couldn't find the placement in my script where it's supposed to go. Not sure why it was missing. So just make sure you go down to the bottom to find it if you want to practice those again tonight. Now, in terms of the heteroscedasticity, like I've said before, and most of you probably are knowledgeable of this, that basically we don't worry about this very much. And that's probably common because most of the time we're not worried about efficiency as much. We care about whether our estimates are consistent more than focusing on the efficiency sometimes. But it doesn't mean that we don't want to know how to do some of these things. So when we're looking at just the standard OLS assumptions, we have the first four that lead to, should lead to unbiased or consistent estimates. But then we also have a fifth that basically focuses on homoscedasticity. Basically, the information that we're getting out of each of the data points, is there more noise in certain portions of the distribution than in others? Now, this doesn't lead to bias. It basically just hurts the way we look at efficiency, how we're calculating our standard errors. There should be some adjustment. So just remember, if you're doing all the assumptions, again, I kind of say this with, cringe in my teeth, but so, the OLS estimates are still unbiased. The problem is, like I said, the usual standard errors, the hypothesis test, the T's test, and the F test that we use is no longer efficient in that sense. Basically, we can't use them, or they're not valid, even asymptotically. So, like I said, I'm going to kind of go through this a little bit quickly, just because like I said before, it's seen as something that's a minor inconvenience for the most time. It's not always looked at very closely. As long as you're sticking to roughly what your area of literature does, if they cluster, if they bootstrap, if they however, there's so many different ways of simple adjustments in the standard errors. As long as you're following that, you're following your literature, then basically you're usually okay. Okay? But, basically people don't care about it as much. They consider it a relic, if you want to call it that way. But basically it's all about a loss of precision. That you might be saying something is significant, but once you make a correction to, how much weight is given to those deviations that you get, once you correct for that, you might actually find yourself as no longer significant. I've seen students basically, they're trying to find something significant, and because they're adjusting in different ways of standard errors, they can get it to say 10%. But when they're using proper methods, it says, it's not significant. So then they want to use the method that's not really proper for their area because they want to be able to say it's significant in some way. So you just have to be a little bit careful and understand what you're actually doing. Now, when we think about the variance properties, we're basically thinking about, if we have this condition, as long as we can say, strict isogeneity, or, in this case, looking at the squared errors given the x's, we're saying that it falls within some constants. We don't care what the constant is as long as it's constant. In this case, if that's true, then this portion can be pulled out. If it's, there is no expectation of a constant, we can pull it out of the expectation. And once we have that, we have a little simplification that leads to basically sigma squared over the variance of x. Okay? That means that everybody, or not everybody, every observation is giving the same amount of information, or is being treated as equal across those outcomes in terms of calculation of the standard errors. When this is not a constant, it cannot be pulled out of that expectation. That's where we have difficulties. And all it's saying is that basically, as you're looking at your distribution, whenever we're running those regressions, basically we're getting more noise and maybe in a different portion of the distribution in terms of that distance from our particular linear line. Okay? It means that we're not being, we need to account the fact that there's different information coming from different portions of that regression line. Okay, so this is where the heteroscedastic errors come in. This is, if you are using cross-section, it is a problem for us. Okay, basically, since we're only seeing one small subsample of the, or not subsample in this case, but one just slice of the sample, we're gonna, for various reasons, we're gonna be stuck with some form of heteroscedastic errors. And in that case, what's going on is that basically we run that the variance of the ui given x is saying that basically each residual is not on average some type of constant. There's more noise or more variance that we're getting in certain portions of our outcomes. Okay. The thing is that there's been literature on this for a while, and basically there are ways of fixing it. You know, we have the perfect world type models that we can try to fix it because we know something about the distribution. Those are usually what we're focused on in the undergrad world or honors because, you know, it's easy to talk about. The likelihood of that actually happening is very small. There's only a few models that actually we can do that with. So a lot of times, even though I'm going to show you these methods, what really is going on is more of a guess on what's how we think the relationship where that noise is showing up. But just knowing the consequences is what we need to care about. So homoscedastic errors are not required for showing that it's biased or unbiased or consistent. So for the most part, we should be okay there, as long as in the linear world. Once we go into the nonlinear, we have more problems with this. It's no longer blue as, or another way of saying it's no longer the best linear unbiased estimator. So in this case, when that happens, we lose our confidence in being able to say anything about inference. And that's why it's important. If you're telling somebody that your results, you know, this is the effect given, you know, this is significance and everything else, and I can say it with some confidence, well, if it's heteroscedastic errors, there is no confidence in that because they're no longer correct. That's why we just need to sort of reweight our outcomes. For the linear models, like I said, this is the weighting thing I'm doing here is mostly to show how it's done. Because when you go into the nonlinear, you'll actually start to, those adjustments are going to be a little bit more important. But for here, it's just kind of showing the methods. So develop a more efficient estimator by reweighting the data. But before we get to that, just to give you an idea of what you are doing when you run robust standard errors. Basically, like I said, most researchers, as long as if they're used to status, like comma R, and then you have robust standard errors, is what you're maybe used to. Well, what it's doing is basically, if you have a cross-section for whatever reason, if it is actually homoscedastic errors, and you run robust, technically you have a less efficient estimator now. Okay? So a lot of times we talk about testing, which I don't think I did here, but you should in some ways test it. Again, not really what people do most of the time. They probably, you know, like I said, I'm trying to give you the idea of what people do in the research versus what we're supposed to do. So just keep that in mind. And then even it should be valid in large samples, though, if we're actually using those robust standard errors. So when we're thinking about the variance using this, basically what this calculation is doing is once it runs the regression, it actually is taking the R squared, R squared, or not the R squared, the residuals from the HJ on all the other variables. So remember what heteroscedastic errors are doing. It's basically there's a relationship of the right-hand side variables in terms of how the residuals are formed. So that's why they would actually run the HJ on all the other regressors. to get these residuals. And then if we have the SSSR from that regression as well, basically we can create an adjustment to the variance of that particular variable's coefficient. So what this is telling you is that this is an after estimation type procedure when you run the robust. One, if you're concerned about heteroscedasticity, you can test for it. I will tell you that most of the time the test is that there is heteroscedastic errors. That's the general. So the question not is about when to run robust, it's more about what's the adjustment that's needed. So in your field, they actually will look at certain types of procedures. So if you're in development, typically we're looking at clustering on the observational unit, because whatever we're looking at in development, typically there's groupings either within the firms or within the the clusters that way. So we would focus on those particular groupings. Like there's some relationship there. If you're looking at economics of geography and things like that, they do a similar type weighting, but they focus on the spatial correlations. If you're in other fields, they're focused on other types of methods that are, particular there. But in cases where there's no underlying sort of knowledge of how the groupings might be, or how I might be able to adjust, and that's when we move into something called bootstrapping. But like I said, it's very field dependent on what we're doing. But it's like, for me, I'm just used to clustering because I know that my observational units, there's a groupings in there because of how the countries are developed or how the housing units are clustered, things like that. So it's hard for me to say, yes, you should do it this way, or no, you shouldn't do it that way. But one of the biggest things you could do at the very beginning is just test it. See if there is some type of relationship between the residuals and any of the right-hand side variables or any of their nonlinear connections. That would then tell you, okay, what's the next step? Well, this is a post-estimation adjustment to the residuals. So basically, it's using the information of the residuals, and then because we don't know what the error term is, right? We don't know the true error term. We can get an estimate of it, but not the true. So then we can use that, hopefully using sample properties because it should be a relatively good sample of the population error term, I hope, that then we can use to check for those correlations. So just to give you an idea of what I mean by this, so basically I'm just going to create a simulated regression. I know that the constant is supposed to be 2, the estimate is supposed to be 4 on x1, and the estimate on x2 is supposed to be 2.5. In this case, I've made a specific model or a specific error term that I know what the relationship is in this case. The relationship in this case is x1 squared. Okay, so that means I've made it sure that there's a connection between the two. So if I was to run this and I was running the standard model, you can see that it's a post-estimation command, so the coefficients are not going to change at all. What's adjusting here is the standard errors. And what happened was, in the first model, without any type of adjustments, assuming homoscedasticity, what I was doing is I was basically underestimating my standard errors according to the robust command. So once I actually use robust, basically it's saying that my standard errors went up by roughly, what was that, 20%? About. So in that case, basically saying I was underestimating. So in this case, because of where the results are, it made no difference. Now, if I changed the simulation a little bit and made everything be a little bit smaller, I could have been on that edge of being just significant versus not. Okay, so you can always make these adjustments, but all it is, and you'll notice that the biggest difference is in the variable I've made related to it, that I've created that connection to it. Okay, so this usually is going to tell you when you run robust versus the standard model, you're going to see those adjustments. Some are going to be very small, some are going to be possibly very large, because it's actually going through and making this calculation for every single variable within your model, because it's actually checking to make sure it needs that adjustment for each of the variables. Okay. And if you actually look at the residuals in its relationship, so these are without the robust, by the way. These are just the standard model. I could actually try to visualize it and run the squared residuals against each of the outcomes. Now you can see that as x1 is increasing, basically I'm getting a higher and higher different or more noise within my outcome, my residuals. In terms of the x2, even though there is a little bit of noise in certain areas, I couldn't say that there was an overall pattern. Okay, so that's where basically you can do you can do a kind of a test in terms of the visual. You can use the white test, or you could basically go through and try to, well, not try, but what most researchers do is basically just assume it's there. I'm not saying one method is better than the other, but you should at least keep that in mind. So this is what I meant by the test. Basically, we could go through and try to run this test in terms of looking at basically taking all the predictions that we get from the model and then actually running those predictions against the residuals. Similar to what we did with the residuals squared against their actual outcomes. Once we have that, we could actually then do a specific test in terms of what I'm calling delta 1 and delta 2. So I didn't actually put the equation there, which is probably bad for me. But what we're actually doing is we're running the model and we're actually getting the prediction of the u hat squared. And then we're actually running it against the constant y hat plus y hat squared. And then basically the delta 1 and delta 2, I should have probably put that there. This is the actual test that we're running against these two outcomes to actually test whether there is some type of relationship between our predictors and the error terms. Now, like I said, I need to check, but I'm pretty sure there is something similar to what we have in terms of time series. The only thing I'm worried about is in time series we typically do, you know, yt and then yt minus 1, yt minus 2. In that case, we know there's a relationship. So that's why I'm not sure exactly how it's structured. That's why I would need to check on that. Okay? But if we do this, we could then basically do a joint test that tells us, are we expecting there to be heteroscedasticity? So in this case, I'm just doing the LM test that works on the chi-squared. My statistic is 21.5, and basically the probability of that occurring is essentially 0. So it basically means that we reject the null. And the null here is homoscedasticity. The reason I'm not going into this too much is because in general, some version of heteroscedasticity is typically present. So this, usually you are going to find a rejection of the null. That's why it's basically good to maybe do this, because it might lead to, you might be able to figure out some of the reasons why it's there. But at least it tells you that whatever method you're doing to make that adjustment, there is some validation for it. This is nothing you would actually put in your research, though, in the sense that this is more of a test for you than it is for what you would put in any type of article. Again, it's more of a generalization, but if for some weird reason, in this case not very weird because I created the data for the simulation, I know what the relationship is. But in the data that you're working with, it's not simulated. So basically you don't know exactly what that relationship is. You can guess if you want. But in that case, you would, whatever guess you're doing, you're focused on something called a generalized least squares model. And what we're doing is basically, if whatever this function is that we've created, if we can pull it out of the sigma squared I, we can basically use it as a weight to the overall regression. And when I mean the overall, I mean the y, the predictors, the constant, and implicitly the error as well. Okay? In that case, because it's actually in this form in the variance, basically we would have to do, once we pull it out of the variance, we'd have to take the square root of this. Because remember, the variance is squared. And we'd actually reconstruct the entire model by just basically dividing through by each of these and creating the y star. So these become our new regressor, or basically our dependent variable, the constant, and also our predictors. And if it's true, then you should be able to show that basically once you do this with the new u star, that you would have a variance that's a constant. So basically we would perform this with the regression on the transform model. The reason I'm trying to show this is basically what's happening is OLS is assuming that whatever information you're feeding it, everything is equally valid. If that's the case, what this transformation is doing is telling, no, that's not exactly correct. Once I reweight it, less weight is given to observations with higher variance, if what I've chosen is correct. The thing I gave you earlier is similar to a structural break. Remember whenever I said something about the Chow test? So that was more of a break between the fact that you're looking at a regression that should we be separating out the groups or should we just keep it as one group? It works along the same line. It's not perfect outcome, but we'd basically be looking for structural breaks within a time frame and not across groups. So it's similar in the same type of model or the tests that we'd run. So if I had changed that earlier example, instead of putting it across gender, if I had like, say, 5 time periods, or even probably more, say 10 time periods, I could then look for differences between two various periods if I wanted to. And it would be a similar structure to those interactions. Is it a fact that I need to account for those interactions across the different time periods, or separating out the two regressions into 2 separate time periods and running it, and then comparing whether they're similar in terms of their information given? So we've sort of covered it, but I covered it from a characteristic standpoint instead of a time standpoint, if that makes sense. But it's the same structure. It's just you're changing how you're thinking about that break. Before I was thinking about it in terms of a gender break. There you would be thinking about it in terms of a time break. I can discuss it more later. Because I work with in other areas that typically focus on characteristics more, I focused on the Chow test in terms of the characteristic, not in terms of what you think about as a structural break of, 2 different periods not being compared across. Then you would want to separate them out versus keeping them as just one, if I'm understanding correctly. Yeah. So I can try to be a little bit more clear after that. In this case, if we run this GLS, basically to be unbiased in blue, as long as we're correct with what we're doing, and basically to be more efficient than OLS on the untransformed model. Okay. So same regression that we did before. These two are exactly what we did before, but this last column now is that reweighted model. Now it's going to be a little bit exaggerated because I know what it was, so I perfectly divided through by what I was supposed to divide through. In this case, you can see that the standard errors are much lower than they were before, even in terms of whenever I had the robust. But note that this constant, so when you do these types of models, one of the things you have to keep track of is not only are we dividing through by the dependent variable and the predictors, but also the constant. It's no longer, in this case, think about what we were actually dividing through by. So I told you that this was equal to x1 squared, right? I told you you need to take the square root of that. Now think about whenever I divide through by this, so the square root of hx in this case, because it was xi squared, or x1 squared in this case, now this becomes x1, right? Now I'm dividing through y by x1, constant by x1. If I do the divide through by x1 there, what happens? It's gone. It's a constant. I'm dividing through by the value it actually is, meaning that it all becomes a 1. That's why you have to keep track of whatever you're doing when these models, because what you're doing right there is you've created a new constant. And now this becomes 1 over the x1. So this becomes the new x1, this becomes the constant. That's why when you're doing these weighted, you have to keep track of what you're sort of dividing through by. Now this is, usually it's not that bad because you don't really use GLS. So in this case, I had to create my own new constant, and this measure really is the 1 over, or the constant over xi. Okay? So that's why it's basically just keeping track of what's going on there. And making sure that, you know, everything is run exactly as it should be. Okay? And also notice that this was a pre-estimation adjustment. These are different than the original, but remember they are considered unbiased, even with this adjustments. Okay? We also have the feasible generalized least square, which is most likely what, if you're doing something like this, typically we don't know what that functional form is like, so typically we would need to create it. Well, one way we could create it is basically assume some type of functional form of what the residual function is. In this case, we could just say that it's equal to some constant plus the predictions of y and their squares. If we do that, then we can actually construct our own h hat. And it's the same thing. Once we have that construction, we basically send it through exactly as before. We take whatever our functional form is, we divide through by the square root of h again, and then we rerun our model. But we are assuming a functional form for this because we don't know what it is yet. But maybe the best predictor of what that functional form is actually predictions of the regression itself. If we use it for the white test, why can't we use it for an estimate of what those residuals might look like or what the functional form is like? Even if we're wrong about the functional form, typically it is better to at least somehow control for it. So this is the next set for the FGLS. And you can see again, basically, we do appear to be doing a little bit better job in terms of the standard errors. There's a little bit of difference in terms of the coefficients, but overall, we should be doing roughly okay, even if we didn't know what the exact functional form of the h of x is. Why? Because sometimes, remember that leaving things alone sometimes is not the best method, but at least an attempt at running it or adjusting those standard errors. And then one thing I didn't mention here is actually running the FGLS, but also including the robust helps out overall. You're attempting to correct, and then you're doing sort of another correction on that correction, which typically says that it's doing a little bit better. Most outcomes. Okay, so that's just what we're thinking about in terms of these corrections, and we have to sort of state the general heteroscedasticity adjustments, the standard ones, before we sort of move into the a little bit more complex ones. What we deal with in cross sections a lot of times is some type of form of clustered data. The noise that we're actually getting, in some way, we see a pattern within it, but it's more related to information from the actual sample that we have. If you want to call it grouping, clustering, in some ways they are very similar. So basically, they're grouped in such a way that unobservables are more likely to be correlated within however this group structure is. If we're looking at something that involves income, then we see that grouping, more variation at certain points within the income distribution. If we're looking at some type of surveys, we see groupings within the way the clustering is for however the survey was taken. When we're looking at international trade, any of those, we see groupings on how the levels of development, or in our case, sometimes in the pair interaction. Okay, so these are all ways of somehow the grouping is there, and that information, if we leave it alone, means that basically most likely we're going to have bias in our standard errors, and basically our inference will be wrong. So just like the example here, students within the same class, individuals in the same region, firms within the same industry. We tend to think we should be able to show that the residuals are sort of in line with each other. Okay? And because of that, the independence assumption fails. If the standard errors are correlated within the cluster, basically we can underestimate the standard errors when there is correlation with the standard errors, but we assume they're independent. So basically our bias is lower than it should be. And it's not going to be always the case. But how those groupings are relative to the mean can make it go up or down. But a majority of what we see is that we're underestimating our standard errors, which then means that any type of adjustment they'll make usually pushes them up, which usually scares most students beyond belief because they go from 2 stars to no stars because those are increased. But it's better that you actually do it the right way than somebody pointing out later that you need to adjust these. So adjusting the clustered standard errors, a lot of what I'm going to talk about right now, I'm going to let the program will be doing it for you. It has the methods to do it. We go into the math about how it goes into the background, but I kind of stay away from that. It's better just to get an idea, the intuition about what it's doing, more than knowing the mathematical derivation of it, okay? So again, I'm going to focus on the intuition a little bit. Okay, so adjusting for clustering. What we call clustered robust standard errors account for within group correlations. So if we have this simulated income data set, if we have clusters of a region, say, and we have 50 districts, and each of those districts has 15 observations. If I was wanting to do this a little bit more realistically, I would have allowed it'll be 50 districts and allow these observations to probably jump around from 5 to 15 just randomly, just so that the clusters weren't always perfect. But in this case, just to keep it simple, just make sure 15 observations in each cluster. If we I simulated the data for years of education with a mean of 12, so basically I'm saying that the average person would have matric. Experience is going to be basically 15 or 10 years of work experience, and it's possible that if in my simulation whenever I did it, basically what I did was if it went negative for some reason, I would force it back up to 0 just to make sure that nobody had negative experience in there. Gender, I'm just going between male and female. Outcome is basically the income. So basically we're going to look at, income is going to be a function of experience, gender, and I'm going to say there's strong clustering. Right now, I'm not really giving it a name, but if you wanted to, you could say that it's related to where the person currently lives. It could be, and that way it'd be like regional. It could be related to information on where they were schooled. I mean, these are all things that I'm just trying to make it general right now. And then I'm going to make a big assumption here, and I'm setting this to 0 so that I can see whether sometimes if the effect is 0, but for some reason it becomes significant, that would show that it's not doing a very good job because I've set it to 0. Okay, so we're kind of, we're basically just trying to illustrate what's going on. It's not supposed to be in any way real for right now. It's just supposed to be giving an idea of how we're thinking about this. From that simulation, if I actually ran it, this is how everything would be grouped in terms of those clusters. Okay, so basically this is just income against education. It's just showing the weighted outcomes across those clusters. Basically, it's saying that there's a lot of people in there and they're going in different directions, and in some ways it's related to your grouping. So from that, oh, hold on, where did I? Yeah. So from that, basically we could run a standard model from those outcomes. Basically, I have our standard, I have our robust, and I have our clustered. You can see there's not much difference. We're sort of focused on the education here. Remember, this is meant to be an after regression. We're making those adjustments after. For the most part, even if I control for the cluster scenarios, because I know there's groupings, basically you can see that in some ways controlling for the clustered is basically some ways closer to what we would expect. Because I am making sure that basically I'm accounting for whoever's in those groups should be, we should treat them similarly across. So we're making sure that everybody, those people in those areas should be treated similarly. And those adjustments. Remember what the standard is. Here we're making the assumption that there's nothing there, that we don't care is homoscedastic. Here we're saying that after that we're just going to make a guess related to the actual variables and make that adjustment. Here I'm saying there's a specific type of guideline I'm using by grouping it. Okay? So in this kind of example, because I didn't make the clustering very strong, and also I didn't really, I could have made it quite ugly and made it, made everything kind of really awkward and made it clustered do very well. But I wanted to make sure that you understand that clustering is just another way of thinking about these adjustments. Doesn't always mean that you're going to get a huge difference. Okay? And in the case of just from the simulation, thinking about the rejection, we can actually show with 1% that all of them are still rejecting the way they should, in the sense that basically at the 1% level. If we're thinking about the 5% in terms of type 1 type error rates, OLS basically is that right? Something's off, sorry. Sorry, these numbers should have been changed. This should have been 3.6, 3.8, and 3.6. I didn't update the program enough. But basically, it's saying that our probability of actually getting type 1 errors is still less than the standard 5% in this case. So even that I know, I created the data, it's clustered. The groupings are in there. But overall, I'm not getting a huge difference in the outcomes that are basically improving the overall results. Okay? So just keep that in mind, that basically all you're doing is tweaking how you're actually looking at the standards. It doesn't mean that you're going to get a dramatic change in how it looks. You can. I could have made this, I had one example of this that made it very obvious that you should have done this. But a lot of times people are so focused on those adjustments that they lose track of the fact that it's not helping out that much. So then that hyper-focusing on that is maybe bad for your overall arguments. So I'm just trying to show that it's possible. So all the methods are performing similarly. So basically, in this case, we're not really getting false positives. Even so, this is where I want to put this. Even so, it remains important to use the appropriate adjustment to the cluster standard errors when data are grouped. So even in those cases where you use robust and you get your answer that you like, but you use cluster because you know there are groupings, you know it is a clustered, there's clustering in that data set. It's not about whether you're getting the lowest standard errors here. It's about performing it in the proper way. Okay? Yes, it might take away from your answer or your inference or what you can say, but it's better that you point it out before somebody else points it out. Okay? So just make sure that to account for the within cluster correlation in other designs or different parameter settings, basically that you're using the proper method. In this case, if you know there is some type of grouped clustering outcomes, you need to use that appropriate adjustment, even if you get better results with the robust or something else. Make sure you're doing the procedures properly. Okay? In terms of bootstrapping, which is very popular as well, basically, why use it? Actually, do y'all know what bootstrapping is? Just ask. Is that a no or? So bootstrapping is something that basically, remember, there's a lot of in the regression that we don't know. We don't know the true model. We don't know a lot of information. We do the best we can with what we can gather. But a lot of times we have a particular method, but we don't know much about its properties. We just have very limited information on it. So basically, traditional methods rely on large sample asymptotics. But Bootstrap offers that alternative when those assumptions might not hold. It's hard to verify, right? I might know that most likely I have clustering. I might have certain properties within the data. But how do I prove that? My intuition might not be exactly right. So a lot of times what we can do is we can try to add some flexibility, trying to improve the reliance of what we're looking at. One way of doing that is just repeated sampling. So basically we can apply this to a wide range of estimators and complex data structures. And basically we don't have to focus so much on the exact variance estimators from models that we could try to derive, but we might not get the perfect answer in that outcome. So one way of doing this is basically, we take a particular sample and we start with it, but then we basically resample it with replacement. So basically, we have something that might not be random, but what if we just take it and then basically keep repeatedly sampling from it over and over again? In that case, if we do that and with replacement from the original data, we can basically compute a statistic or calculate a statistic that's basically related to beta or our x's or even, in our case, our standard errors. If we perform this, say, 1,000 times, and don't worry, the computer does it for us for the most part. Then once we have that, we're basically summarizing, we use the empirical distribution from the bootstrap. So basically it's repeated sampling over and over. We're not giving any instructions other than repeated sampling of some size. Give me 1 second. But from that, we can basically estimate the standard errors, construct confidence intervals, and perform hypothesis testing from our hopefully random sample from the repeated bootstraps. We don't want to give it any instructions. We say, we don't care, just randomly start picking out from the sample, even if it's repeated. Basically, you pick, once you picked it, you hold it, and you throw the other one back in, and then you go and pick again. You can possibly get repeated outcomes from the same observation, but that's just one sample of the 1,000 or 10,000, because you're doing this repeated times. So your data might not be exactly random. But what happens if I take whatever your data is, 1,000 observations, and whatever is going on there? But if I repeatedly sample from it without giving any type of direction, then basically it's randomly picking. Then in some ways it starts to bring in those properties of the being a random sample, right? Even though before it might not have been, but if I keep doing it over and over again, because I'm not actually telling the computer to pick particular outcomes, it should hopefully start to get the properties of something we would consider random. It's trying to create randomness from something that's not random in a way, a general way of talking about it.
My thing here is that instead of constructing, why don't you just increase the sample size?
What do you mean sample size?
Because for example, maybe from 1,000 or for example, 600.
No, so I wouldn't put a restriction on the sample size. If you have 10,000 observations, my sample coming in, the one I bootstrap with, will be another 10,000. It's a random generation from that. You can restrict it if you wanted to, but I don't. When I've done this before, I've never restricted it. I'm saying just go through and pick 10,000 observations of my 10,000 observations and basically just keep repeating. Sometimes I do see models like for training stuff like that do pick, smaller samples, but in general, because I don't do this as much, I usually, when I've done it in my work, I've always just used whatever the sample size is. I want you to randomly pick out of the sample and create the same size data set. So yeah, I'm not restricting in that way. I'm not going to say it doesn't happen though. It can be, there could be reasons for that. So from this, basically, we can get some type of sampling distribution that we hope for will be in some random, especially if we're doing this, say, 10,000 times. It is basically, suppose we have a regression in our simple set. We relying on the OLS variants, our standard outcomes. So we assume that that's what would, or I'm calling it the naive approach, basically, in this case. Basically, I'm just assuming it's homoscedastic. Instead of that, we can actually look at the bootstrap approach and basically say, let's resample all the rows with replacement, say however many times, and then re-estimate beta on each instance as we go through. So I basically tell it to randomly sample from that outcome, estimate beta. Do it again, estimate beta. Do it again, and so forth, over and over and over again. This is sort of what we remember how we've done when you've taken an econometrics course before. We always talk about as n approaches infinity. We're kind of resampling over and over again. It's sort of that same type of mindset. Basically, we're just here's a new sample, estimate, new sample, estimate, and so forth. Once we have that, we can actually calculate the variance of the betas across all of the replications. Okay? And if we do that, basically, it might perform a little bit better. I'm not guaranteeing it will. But it has some of the properties that we do like. That basically it should be in some types of new random sample, or sampling distribution in this case. So when does the bootstrap work? A lot of times, basically, it's when you can treat the sample as if it represents the population distribution, and also when the statistic of interest is sort of, well defined for each of the resampling. So what we're just basically saying, it's not going to be poorly behaved in the sense of that we can treat whatever sample we originally had as being from the population distribution, which we make that assumption a lot. When we take the data, we're assuming that it's coming from a larger population distribution. The statistic of interest is well defined within each of the resamples. So basically, we're not getting variation in the sense of how we're defining it across each of the resampling. If education in one sample, when we resample, it's still having that same type of definition. So if the original sample doesn't capture the population's variability, very well, in the sense that for some reason, when we took the sample, in the primary sample, we had a large range within our education outcome. When we're resampling, for some reason, instead of being, from 0 all the way to 16, it's for some reason, 8 to 10. It's not defined in the same way. It's not got the same amount of range or variability. That would be a problem for us in that sense. And then basically we can get to sort of misleading outcomes. And then also we can look at under general conditions, we can say that the bootstrap is consistent for estimating sample distribution. So usually as long as our N is large and everything is most likely well behaved, so we can say that, and under those conditions, then we can say that whatever's coming out in terms of the recalculation of standard errors or the statistic, it should be consistent. Okay? These are things that we already consider most of the time, but it's something that's a little bit stronger here because we're trying to create a new sample distribution by doing this repeated sampling. We're not relying on the variance formulas of OLS and stuff that are based on theory. So we have to be a little bit cautious, but as long as our N is very large and we have enough variation and most of these things hold, we should be able to say that the bootstrap estimates should be consistent. Okay. These are all different ways of actually going through and trying to make the calculation or remove some of the bias we get within the standard errors or even sometimes the estimates. I'm using it for standard errors here, but it is used for estimates as well. Okay, so I'm not going to say it works on every plane, but it is one of those options. And then this is just the general bootstrap. There are several versions. I don't know if anybody's heard about the wild bootstrap. There's also other versions of this. So trust me, if you get into this work, it can be kind of varied, and this is just the basic of starting into that literature. Okay? But again, if you're so focused on this, you got to stay in line with whatever your literature is. Not saying that you shouldn't use it, but if you're on a tangent just because you're not getting the significance that you want, it might be better to go back and look at the data and how you're looking at the modeling structure than trying to jump in to just find various ways of calculating the standard errors. Might be better to sort of go back one step before jumping into this area.
What can be considered as a very small n?
So that again, I know I keep pawning this off on different things, but it sort of depends on the field you're in. Small n in some cases, in some fields, could be as much as 50. Large n could be as high as 500. That's some fields. Other fields, in terms of like international trade with gravity, I sometimes work with a couple of million. And I've seen research that actually tries to show that even when they had 2,000 observations, they still had bias in the standard errors. So sometimes it's sort of field dependent. If you want an exact answer, I would say as long as you're in the thousands, you might be getting higher and higher in. But you also, we're not really talking about right now, we're not talking about the panels as much either. There's also a problem with, how do you see in terms of N as well as T? So there's a complication there as well. So I can't say this is the N you need. It's more likely, again, based on the area that you're in. Yeah. But I can say from most of the examples I use, I've usually considered anything less than, say, 500 to 1,000 N as being small. But don't take me on that if you're in a field that they're using millions of observations.